In this video, we're going to make things a little bit more general than we've been doing recently. In our recent tests, we were looking at series where all the terms were positive, right? And we had a bunch of tests that would apply in that situation. Well, the thing about infinite series is when some of your terms are positive and some of them are negative, things can get, well, let's be honest, a little wonky, right? So yes, I used the word wonky. It's just really strange, right? Well, we're going to focus on a type of series that has positive and negative terms known as an alternating series where things, yes, are a little strange, but not quite as strange as they could be. So we're just going to look at one type of infinite series where not all the terms are positive, right? And these are called alternating series. So let me start by giving you an example, a really simple example of how you can create an alternating series based on the series that we've looked at before. All right, so I'm just going to write down one of our famous series. You might remember this one. It's a P series, but specifically this is our harmonic series, right? So when P is equal to 1, so we have our harmonic series. Let me just say here P is equal to 1. Well, suppose I took this, right? So you know what the harmonic series is. It's really just the sum of the reciprocal of the integers, the positive integers. Well, suppose I change my harmonic series just by adding an additional factor here. So I'm going to multiply this term by another term, and the term looks like this. Let's say we start with negative 1 to the k plus 1, and then that multiplies 1 over k, right? This now is no longer our harmonic series because it's going to have some negative terms. So let's write out a few of those terms just that we can see what's going on here. So when k is equal to 1, the exponent will be 2. In fact, let me not skip too many steps. So this is going to be negative 1 squared times 1 over 1. And then the next term is going to be negative 1 cubed times 1 over 2, right? So this is what I would get when I plug k equals 2 into my summand. If I plug k equals 3, then I'm going to have negative 1, oh, not equals. It should be a plus sign. All right, so then this will be negative 1 to the 4th power times 1 over 3. Let's write down one term, and then we'll do our dot, dot, dot. So then this is negative 1 to the 5th power times 1 over 4, and so on. Right, so that's our pattern here. If we now stick this little factor right in front of the 1 over k. So now let's simplify and see what happens. Right, well, negative 1 squared is 1 times 1 over 1. That's all equal to 1. Negative 1 cubed is negative 1 times 1 half gives us negative 1 half. And then negative 1 to the 4th is 1 times 1/3, so that's a positive 1/3. And then the next is going to be a minus 1/4, and then plus dot, dot, dot. And so you can see what happens. Look at the signs, SIGN. They now alternate between positive and negative, plus, minus, plus, minus, plus, right? Just by putting this additional factor in. In fact, some people refer to this as the alternating factor. Right? And it's this additional factor now that gives us some terms that are positive, some terms that are negative. In fact, you can loosely say that half the terms are positive and half the terms are negative, right? And this will be our approach. So we are going to look at series that where If you look at this part, so let me kind of highlight this part. This looks like the terms that we saw in previous series that were all positive. So we're still going to refer to this as our a sub k, right? But then our a sub k is going to be multiplied by a certain factor that produces the plus or minus pattern, right? And that's one way to do it. Another way to do it, let me just again show you with if we take our harmonic series and put a certain factor in front of it, what happens? Well, let's say instead of using -1 to the quantity k plus 1, I could have also used -1 just to the power k and still have my 1 over k. And what that would do, it would shift, or you can actually think of it as a switch, where you flip a switch and turn all the positive terms negative and all the negative terms positive. So because what happens is, if I start by plugging k equals 1 here, right, then -1 to the first power is going to be -1. So instead of having a positive 1 as your first term, you're going to have a -1. And then the alternating pattern continues, because when I square this, right, if I plug k equals 2 in and I square my -1, then I'll have a plus 1/2 minus 1/3, and then plus 1/4, and then the next one will be negative something. Well, it'll be -1/5, but I'm not going to write it. Just dot, 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 right? So these are the two standard ways that we can take our previously looked at series where all the terms were positive, and we can now create what we call an alternating series. So let's go ahead in general and write it down. Right? So in general, an alternating series. So an alternating series my strokes are a little bit, talk about wonky, right? An alternating series has one of the following forms. So it has one of the following forms. And what do they look like? Well, it's basically now just, I'm going to, instead of having a specific function for my general term, I'm just going to use our generic a sub k. And what I'm going to stick in front of it is, now, again, it depends the starting value for your k, so I'm going to leave it out. But it's basically either -1 to the k times a sub k, or -1 to the k plus 1 times your a sub k. Right? So it looks like this, where, and we're going to assume that our a sub k's are still positive. Right? So if you strip away the plus or minuses, you're going to be left with all positive terms. Right? So where a sub k is assumed, oh, this is not great, so assumed to be positive. All right. Now, if we just kind of go back up to the example that we started with, I gave you, or reminded you, I should say, of the name for this special P series, the harmonic series. And now over here, where we've included this alternating factor, then this, we refer to this as the alternating harmonic series. And this is actually a really interesting series, because it you know, if you like math magic, in a not too distant video, you're going to see some magic done with this alternating harmonic series, right? And it's not just special to this one, but it's a good one to kind of highlight some interesting properties that these series will have, right? But before we get to those more interesting properties, we want to go back to the basic question about convergence or divergence, right? So now that we have, a series where some of the terms are positive or negative, the question is, how can we determine if they converge, right? Well, it turns out that we have a nice theorem for that, right? Don't we always have a theorem for this? So we have a theorem, and this one is called the alternating series test. So alternating series test, and it tells us, it gives us the criteria that's required for one of these, and it doesn't matter which form, right? Whether you have the exponent of k or the exponent of k plus 1, this test applies. So here's what it says. An alternating series, and it could be either one of these forms, converges if the following conditions, and there are two of them, the following conditions are met. All right, well, what is the first condition? So I'm going to write it out in a couple ways, but it basically says, so assuming we start with k equals 1, right? So like a sub 1 must be greater than or equal to a sub 2, which must be in turn greater than or equal to a sub 3, and dot, dot, dot. What this is saying is that the positive terms here, so this is saying, so that is, i.e., a sub k must be decreasing, right? So a sub k is a decreasing sequence of terms. Right, now I know we're using the word sequence and series in lots of, in a sort of a combined way. But remember, what this is basically saying, a sequence is just the terms themselves, right? And if that sequence is decreasing, then we're on the right track. But furthermore, we have to make sure that not only are they getting smaller, the terms are getting smaller, but they have to approach 0, right, in a limiting sense. So not using x, we're using k. So the limit as k goes to infinity of a sub k, that has to be equal to 0, right? So, in summary, let's just say what this alternating series test requires. If you have, and we'll say it in one sentence, if you have a sequence of positive terms that are decreasing and are approaching 0, then the alternating series of those terms must converge, right? So your positive terms are getting smaller and they're approaching 0. If you put one of these alternating factors in front of those terms and then add them all up, right, the positive and negative terms, you'll get that series to converge, right? So again, the proof of this isn't very difficult, actually. It's not a terribly difficult proof, but we're going to skip that and we're going to do some examples because I'm sure you're dying to know what are the examples that are related to this, right? Okay, so we're going to do some examples. And again, the idea is, I'll just point out the fact that these are alternating, and we're going to apply our test to see if the alternating series passes both of these tests or not, right? And here's the thing about these two conditions that you can still see. If, for instance, again, and it comes back to our ability to do limits, if we can look at the general term, right, the thing that is multiplying the alternating factor, right, or is being multiplied by the alternating factor. If we can do a little mental limit calculation, and if we see that the terms don't approach zero, then we're done. We don't even need to check decreasing, right? And we'll do a couple examples so we can see different ways that you can check that a sequence is decreasing. All right, so here's our first example. Let's say we have this series. And I'll just start this one at k equals 1, and then I'm going to put my negative 1 to the k plus 1. That's going to be my factor. And then I'm going to have 2 plus 1 over k. So it looks like this, right? Now, let's say I were to write out these terms so you could see what they look like. Well, when k is equal to 1, we'll have a positive 1 there. And then I'll leave the parentheses just so you can see it. So then you'll have 2 plus 1 over 1. And then the next term now, when I plug k equals 2, then I'll have negative 1 to the third power, so then I'll have a negative coefficient here, and then it's the quantity 2 plus 1 half, and then plus 2 plus 1 third, and then I'll do one more, alternating again, negative quantity 2 plus 1 fourth, and then plus dot, 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 right? And that's what it looks like. And we want to know if we continue this pattern, will our terms converge to a fixed number? Now, so let me kind of highlight something important. Here is the a sub k. And I can look at this and I can see right away that condition B, the second condition, that as k goes to infinity, the terms have to approach 0. This set of terms, it does not satisfy this condition. And we can see it. So I could just say the limit as k goes to infinity of 2 plus 1 over k, then this is not indeterminate. We know that the 1 over k approaches 0. So that limit is equal to 2 plus 0. So that's equal to 2. So because the terms approach positive 2, and 2 is not equal to 0 last time I checked, then we don't even have to check the decreasing part. In fact, we can look at it and see that what's in parentheses is not decreasing, right? No, actually, no, I'm sorry. It is decreasing because this is 3, then this is 2 1/3. I'm sorry, 2 1/2. This is 2 1/3. This is 2 1/4. So yes, what's in the parentheses is decreasing, but it does not approach 0. So what is our conclusion? Then we can say that this alternating series diverges, right? So this alternating series diverges. Right, and there you go. So it doesn't pass our second condition. And again, you can look at it. If it looks like something that you can compute a limit quite quickly, start with that. And then if it passes the limit test or the limit criteria, then you can look at the decreasing property. All right. Let's try another one. Let's take a look at something like the sum as k goes from, let's say, 1 to infinity. And now, just for fun, I'm going to have negative 1 to the k, and then I'm going to have k over 3 to the k. All right. So again, what would these terms look like? Well, when k is equal to 1, you'll have negative 1/3. And then when k is equal to 2, you're going to have a positive 2 over 9. That's 3 squared. And then when k is equal to 3, you're going to have a negative 3 over, and I'm not going to reduce this. 3 cubed is 27, and then plus, then you'll have 4 over 81, and then you'll have minus, and I'll just put my dot, dot, dot. So that's the series under consideration now. Does it converge? Does it diverge? All right. So let's take a look at, here's our a sub k, right? And so let's write that down. And we have k times 3 to the k. So I'm going to go through and establish, or check, I should say, both of the criteria in order. So the question is this decreasing, right? Well, there are several ways that you can determine if a sequence of terms is decreasing. But remember, that word decreasing came up quite a bit in Calc 1, where you learned how to test to see if a function is decreasing. And here we want to know if this function, for instance, is decreasing for all values of k that's greater than or equal to 1. So we don't want to just test a couple. I mean, you can look at these fractions and say to yourself, hey, they look like they're decreasing, because you have 1/3, 2/9, 3 over 27, 4 over 28. So it looks like the fractions themselves are getting smaller, but you can't just look at these and just make a guess and say, oh yeah, it's going to be this way forever. No, we have to make a more general observation. So here's how we can do this. So using derivatives, right? So using derivatives, and I will remind you, or maybe some of you already remember how we use derivatives to check if something is decreasing. So I'm going to rewrite a sub k. Instead of having it as a fraction and thinking about using the quotient rule, now I'm just going to write it as a product. And then, so I'll write it as k times 3 to the negative k. Just bring up that denominator, change the sign. Now let's look at the derivative of this, right? And if we can identify a very key property about the derivative, that might tell us if the series is, or if the sequence is decreasing or not. So I'm just using this to represent our derivative. So using our product rule, derivative of the first is 1 times the second. We have, not e, but 3 to the negative k. And then plus the first times the derivative of the second. So we have to remember this. This requires the chain rule. It also represents our exponential rule from Calc 1. So we're going to get back the same exponential function, but because it's an exponential function with base 3, we have to multiply by the ln of that base. And then I have to multiply by the derivative of the inner function, so I have an additional -1 there, right? Okay, so let's look at this derivative. Notice I have a 3 to the negative k in common, so I'm going to factor out the 3 to the negative k, and then in parentheses, I have 1, and then this negative sign is going to change that to a minus, and then I have a k, and then times the ln of 3, right? And what happens is, for k, here we go, for k greater than or equal to 1, what we have in the parentheses here is always negative, right? So I'm going to write that down. So for k greater than or equal to 1, in fact, there are two things we can say. 3 to the negative k is always positive, right? This is an exponential function, always positive. And then what's in the parentheses is always negative, right? So, and 1 minus k times the ln of 3, that's always going to be negative, right? How do I know this? Well, when k, so what you can do is you can think about this kind of as so this constant is always 1. The ln of 3 is already bigger than 1. When k is equal to 1, I will have 1 minus the ln of 3. That is something negative. And if as my k gets bigger, like as k moves from 2 to 3 to 4 and so forth, I'll be subtracting something that's bigger from 1. So that difference is always going to be negative, regardless of what k is. And this is the type of statement we want to make because we want to say that the sequence is always decreasing. Well, how can we say that? Well, think about this. What this is saying, so therefore, our derivative is always the product of something positive and something negative. So basically, I'm going to write this. Our derivative is always going to be the product of a positive term and a negative term. That results in something negative. And if my first derivative is always negative, then it means my original function is always decreasing. That's the big, well, one of the many big concepts from Calc 1. So therefore, right, a sub k is decreasing, right, for all, kind of redundant here, but k greater than or equal to 1. All right? So that's good. I'm going to put a green check mark here, right here, and say that is our first property that is now satisfied. Next up, we want to see if the limit of this as k goes to infinity, right, do these terms approach 0? So yes, they're getting smaller, and we can see them up here getting smaller, but the question is, do they get small enough, right? How small is small? Well, for us, infinitely small is 0. So let's take a limit as k goes to infinity of our terms. 3 to the k. Well, this is a wonderful indeterminate form. I think it's set up perfectly for L'Hopital, so we're going to do our L there. Our limit as k goes to infinity. So take the derivative of the top. So now this is not the quotient rule. Remember, L'Hopital just says take the derivative of the top and the bottom separately. So when I differentiate k, I'll get 1. When I differentiate 3k, like we did earlier, we have that special rule for exponential functions where the base is not e. You get back the exponential function, and then you multiply it by the natural log of the base. But the important thing now is this is not indeterminate. The numerator is a constant, so this approaches, we like to write our kind of, in this case, 1 over infinity form, but we know when the denominator gets arbitrarily large and the numerator is a constant, for instance, then the fraction gets arbitrarily small, so that fraction approaches 0. That's another check mark, right? And we just need these 2 check marks for our alternating series, right? So again, in summary, we have an alternating series, right? And let me go back up before we summarize and conclude this hopefully informational video for you. It was this factor alone that told us that yes, we can apply this test. And then we apply the test by using the a sub k. So notice technically we never really did much with the -1 to the k. That's just more to see, okay, can we identify these alternating series? And then once we answer that, yes, then the question is, can we do what we just did and apply the alternating series test? And once we get our 2 check marks, and so here's our conclusion. So this alternating series converges. What does it converge to? Your guess is as good as mine. Well, this one I would say I kind of have an idea what it converges to. Again, we got some nice fancy math tricks, but basically, let me go back up one more time. Yes, if you continue this process indefinitely, adding these positive and negative terms, we will get a number out of this. What is that number? Well, that's for me to know, and you to find out should you ever get to a few more advanced math courses. All right? So that's our alternating series. So hopefully now at the end of this video you're able to identify what an alternating series is and then apply this test. And if you're good on those 2 points, then yes, kudos to you, and I'll see you in the next video.